Similarity is all about the idea of shapes being the same. We spent so much time on congruence, meaning identical. Similar, on the other hand, again, means that the shape is preserved. And so doing that, we don't need isometric motions, we need similarity motions or similarity transformations. Now, similarity, again, means that we are maintaining the shape. So of the motions that we know, which ones maintain shape? Of course, the translation maintains shape, translation. What else? Of course, the rotation maintains shape. Of course, the reflection maintains shape. So now you're saying, wait a minute, we're just listing out the isometric ones one more time. And you're correct, these are the isometric group. But somebody else maintains shape, the dilation. And so these guys together, this group, is known as the Similarity Transformations. So if we look at this in a Venn diagram setting, we see here how our friends in here are those isometric ones. And then when we add the dilation, we now have the group that we call the Similarity Transformations. And by using any of those, we maintain shape. Now, when we talked about two shapes being congruent, we learned a few important things, that the way we ordered it greatly mattered. That if I wrote triangle ABC is congruent to triangle DEF, what that meant is angle A had to match angle D exactly in terms of size, and angle B had to match angle E. And of course, angle C had to match angle F, as well as the connecting parts of AB. That segment would be identical to DE. Something similar to that, similar, that's a pun, something similar to that takes place with the similarity transformations. You also have things that are the same. So if we found out that two things are indeed similar, say this little guy and this bigger guy are similar, what would that ultimately mean? Well, it would mean the angles would be equal in those two guys. Because AA, or angle, or that expansion by a dilation, maintains angles, is something that we learned. Very important. Similarity preserves the angles. Now, the second phase of that is it doesn't make equal sides, does it? It makes proportional sides. So everybody is times a scale factor. So if you took little ab and you multiplied it by k, you would get DE, so it got a little bit bigger. But you would multiply everybody by that same amount, therefore everybody is proportional. So in this case, when we say they're similar, it doesn't mean they have equal sides. It means the proportions of each of those ratios, each of those sides is the same. And they will all be exactly the value of that scale factor. That's an important thing, so grab that characteristic. Angles stay the same, and then the sides are proportional or in ratio. We did something very similar to this. I keep using the word similar to this in that when we were talking about congruence. And we follow the same kind of logic, that if we talk about angle M, then we must be talking about angle A. And if we're talking about, let's watch this, the ratio of RG, all right, RG, the back two, to BC, the back two. All right, so we're going from the red guy to the green one. So now we go GM here. We must partner up in this guy. So it must be CA. Do you see how important it is that these were written in a particular order to inform us of the order and values? Let's do that again. So in this case, I am going MR. All right, here's MR. And I'm comparing it to MG. Oh, okay, MR to MG as, let's see, MR. So that would be AB as to AC. So I'm able to see that this must be AB. So in this case, there was no diagram. I don't need a diagram, though. As long as I have the proper similarity statement, I can work from that. In the final question, we want to prove or establish that they are similar. And the way you can do that is you can map this guy or this guy onto each other. If I can take this guy and land him exactly on this guy using only similarity transformations, then they would have to be similar. So there are different ways to do this, but I'm going to slide this right into this spot. So to slide it over, that would be a translation. And it looks like I've got to go 8 to the right. So 8 to the right. And what that would do is it would put me right into this position right here. And let me just fill that little guy in. Basically, we would be right into this spot here. Now, from here, what do we do? How do we make it bigger? Well, you know what to do. We need to expand this out, right? We need to dilate it about the origin. And we might say, well, how do you know how big to dilate it? So I look here and I see I'm at a length of 2, but my final length needs to be 6. So I see that I need to dilate this by 3. And so the first step I would do is translate it over into this position. And the second step I would do is translate that. And so maybe to be better off, we might say ETHP is what we translated. And then we would dilate that guy's image by a scale factor of 3. And bam, we would land on that guy right there. Perfect.